as a simple form method. So let me reset everything. Bluetooth, define now Bluetooth uses a pairing of the devices. Okay, so this way we have a closure-form, in some cases closure-form estimators, and we have some asymptotic properties. So we start to discuss about the maximum likelihood method. Now the maximum likelihood method is, I would say, very simple in its essence. Okay, so because it states simply that if you want to make a maximum likelihood estimator and you want to get the maximum likelihood estimation, estimator is the function. Okay, so the function which is enabling the possibility to estimate a set of parameters. Remember, the set of parameters should be deterministic, so should not be random, or at least even if there might be random, but you assume as a deterministic within the framework of the problem that you are solving. Now, and we will see later how to handle in case you have a random parameters. So now the system works in a very simple way. What we need to write, the probability density function of the observation, which is of the data, x. This probability density function should be, depend, so it's parametric with respect to the set of parameters. Now, this parametric representation, okay, is indicated by this vertical bar here. So I need to write essentially. I need to write the probability density function of my observation, okay? And these probability density function, in some way, is parametric on the set of parameters that I want to find. So these set of parameters are the parameter of the PDF. Now, the maximum likelihood method, which is very simple, it says, if I can write this, perfect. Then, what I can do is, I can plug my observation into these parametric probability density function, and then maximize it. Because if I maximize with respect to that observation, to the specific observation, I can find the set of parameters that are maximally likely, that are describing best the observation. So, this means that the maximum likelihood method is taking, so if you want, you can write it this way, is the argument that maximizes the probability density function of x when x is equal to x0, which is the observation, parametrically with respect to data. Then my maximization is with respect to data. Okay? So when I write in this way, and I don't remember if we discussed, so when I write this way is the argument that maximizes this function. Okay? And the maximization is carried out with respect to data. Okay, what is the subscript here? Now, let's illustrate a very easy way. So let's assume that now the set of parameters is 1 and the number of data is 1 sample. So very, very easy. Now, that means that, the likelihood function, which is the probability when I plug in my observation inside, so it's x equal x0, okay? And, I I can describe my probability as depending on x and theta in a generic sense. So this one is, I mean, if you think about it, it's a function of two parameters. Because, you know, it's a function of two values. One is theta and the other is x. So this, you know, if I try to describe these hypothetical functions that now depends on two variables, x and theta, I get something, you know, that I sketch this way. Look at here. So I sketch it this way. This is the function. Now, so in this axis, I have the data, and in the x-axis, I have the parameter. But you know, when I illustrate it this way, I'm not choosing any data. So I'm not taking any data. I'm just writing this function in a generic sense. Now what I do is I make my one observation, which is x equal x0. Okay, so I make this one. I make these observations. Now when I make these observations, what I'm looking at the set of parameters that are maximally lucky, which means, you know, describe the set of observations with the maximum probability, if you like. So, in other words, what I do is, since this behavior, this contouring, okay, is like a mountain, so this behavior is in some way cutting, you know, you remember the conditioning, cutting, okay. These 2D function in this way. I want to find a set of parameters that are maximizing, okay, the corresponding probability. And this is a set of parameters is the following. So, you know, if I cut it here, well, it's not the maximum because I have a contouring. Look at here. So if I cut it here, my contour is that, and the contour is representing the corresponding probability density function. So if I cut it here, no, here. I need to cut here because, I mean, when I cut it here, that is the maximum probability. Then it's going down again. So in this way, this parameter, which is representing this set of parameters, is representing the value, which is maximizing this new function, which is the function when I decide when I set the observation or the data to be x equal x0. So, in this way, we find a new estimator, and the estimator is the estimator which is maximizing this new function. Now, so what I need to write the probability density function of the data. That's it. So if I know how to write the probability density function of the data, and remember, the randomness in the data can be due to the noise, or can be due to some other aspect. Okay. So this means that we need to know something on the statistical description of the model, of the data. So we need to know that our model is deterministic and our data is random in a certain sense, and then we can write it, we can write the random part or the corresponding probability density function. Now, so let's see what is the benefit of this estimator. Now, the benefit of this estimator, okay, which is essentially very simple. Now, the benefit of this estimator, okay, here, so selects the more likely model parameter maximization is okay. Let's discuss it in a minute. The good news is that the maximum likelihood estimate is asymptotically unbiased, at least asymptotically. So usually, if I make the estimate by using the maximum likelihood method, so the estimate is unbiased. And there is another nice property. The nice property is the following. If I choose a very large number of samples, which means that if I look at the asymptotic property of the maximum likelihood method, I can state that the maximum likelihood estimate that depends on x. And remember, x is n times 1. Okay, so it's the number of my data. So if I make my estimate, this estimate is behaving as, so it's going as a normal, so as Gaussian, with the mean that is theta, which is a true theta, and with a covariance that is the minimum covariance that we can get, which is the covariance that we can derive by the Cramer-Ram model, which is something that we will discuss. Now, this property is for n going to infinite, which is totally useless for our case. So we say that this property holds when we have a very large number of samples, large enough number of samples, which means that if we don't have a very large number of samples, this might be a very good approximation. Now the main reason for using the maximum likelihood is this guarantee of efficiency. So in this way, our estimator is efficient because it's using the data at best, because the estimated value are biased, and the covariance is achieving the lower bound. Okay. Now, everything is nice up to now. There is a bad news. The bad news is that if I want to find the maximum of the likelihood function, most of the case is not trivial. So you need to use numerical methods for that. Okay? So that's a bad news. So that means that I don't have a very nice formula. I need to use optimization tools, optimization programs. The last comment I have to say on that is that when n is going to infinite, so it's going this way. Well, if n is going to infinite, it means that the size of the data, so the data is becoming very large. So if the data is getting very large, it's big, okay? So if the data is big or large, the maximum likelihood is optimal. So that's the good news. And by the way, we will see that when we treat about the pattern recognition methods or classification methods, that knowing that the behavior of the parameters or of the distribution is Gaussian, it's going to be very helpful. And this is something that we will see. Now, let's see how to write it, because how to now, is, let me say, kind of abstract, okay? So let's see how to write it. So let's look at a very simple way, which is an additive noise model. Now, in case my model is additive and not white, additive noise. So in case the noise is just additive, my description of the likelihood function is very, let me say, kind of simple. Now, what is the additive noise model? The additive noise model is when I have my data, which is depending on the model, okay, which is as theta. Theta is the set of parameters that I need to estimate, and then W is representing the model, the noise. So, if I want to write the probability density function of X, now when I indicate with this conditioning, this condition is not a condition, it's just indicating that, the PDF of X, okay, is written for theta as a parameter of the distribution. Now it's a kind of it's a kind of ping pong, because theta is the parameter of the model, but theta at the same time is the parameter of the distribution. So it's it takes two roles. Now for this special setting is something that we have already seen. So the probability density function of X is simply the probability density function of the noise, where S theta is acting as a mean. So, when I have the probability density function of the noise, where I just move the mean, by S theta. So the way I write is the following. So I write it as a probability density function of the noise when x is equal to, so the argument is equal to x minus S theta. So I just move the mean, corresponding mean, something that we already see. So, so now, once more, in many settings, we write the Lagrange function by revisiting the Lagrange by the log Lagrange. So, what is the log Lagrange? We are using the logarithmic of the Lagrange function. The Lagrange function, okay, which is so the Lagrange function, which is the px on theta, okay, and then you know what I can calculate the logarithmic. Now the good property of the logarithmic is that if theta is maximizing the function, is also maximizing the logarithmic, okay. Now the property can be used because the logarithmic is monotonic. So since the logarithmic is monotonic, any maximizer of the function, which is the log Lagrange of the Lagrange, is maximizing the log Lagrange. Okay? So you know, using the log Lagrange in many settings is very helpful, and this is very helpful for Gaussian distribution. Now, let's see a little bit more. Now, let's start with a set of general cases. So the set of general cases, I start with the first general case. Now, this is the most general that ever. So let's assume that x, okay, so the data is in general Gaussian. So if the data is Gaussian with a mean that depends or not on the parameter, and covariance that depends on not on the covariance, then my Lagrange, I would say, is kind of easy because I only need to write the probability density function of the multivariate Gaussian distribution, which is, I go, you know, on the back of a few pages back, and I copy here, except that, you know, when I copy C of theta. So it is the determinant of the C of theta, and then there is this exponential part with, you know, with the covariance indicated here. The covariance here is C of theta. Okay. Now, so if theta is embedded, so is included in the covariance and in the mean, well, I mean, maximizing this function is not that trivial. So let's make some special cases. Now, special case number one. Let's assume that my model is a additive noise model, where I have, you know, my model and plus noise. Let's assume the noise is Gaussian with a zero mean and covariance CW. CW is known. Okay. Let's assume that I know the covariance. I don't know what is the noise, but I can describe, I know the covariance of the noise. Now what I do, I go back and I just write using the formula before. This formula, okay. And then, you know, what I can say is that, let me show you how I can get that. So if x is equal to S theta plus W, and W is normal with zero mean and covariance, okay. So what is the probability density function of x? So the probability density function of x is normal with mean as theta and the covariance CW. Okay. Now I can write the corresponding Laplace function this way. So if I want to make a mapping, I can say that here the covariance, which is replacing C of theta here, okay, is not depending on theta, and the mean, which is embedded in the model, which is equivalent to mu theta, is depending on theta. So, you know, I mean, it's kind of straightforward to take these relationships and plug into them. So anyway, now this is the probability density function written parametrically according to the model. This is the Laplace function. So in order to find the optimal solution, then I can calculate the logarithmic for that. When I calculate the logarithmic for that, then I have, you know, so I indicate which is calligraphic L, and so it is it's equal to, now there is some scaling factor, okay, and then there is 1/2 logarithmic of the determinant, good. Then, you know, when I take the logarithmic for that, you know, the logarithmic and exponentially goes away. Okay? So what happens is that I have -1/2, and then I have x minus s theta transpose CW to -1 x minus s theta. So, you know, assume that now I need to maximize this one. So maximizing the likelihood, maximizing the log likelihood is the same. So what I do, I need to maximize with respect to theta this one, which means maximize the other. But you know, this one does not depend on theta. This one does not depend on theta. So for the maximization purpose, this and this is irrelevant. Okay? So what remains is -1/2 blah 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 blah. But you know, if I need to maximize minus something is equal to minimizing the argument. Okay, so which means this one. So the maximum likelihood is equivalent to minimize what I indicate in yellow. Okay? So maximize that is equal to minimize with respect to theta this one. Now, so I simply take and copy down. So it goes here. Is photocopy, okay? My function to be now minimized. Remember, I'm minimizing this because I'm maximizing minus something. Is it clear, the story of, you know, maximizing minus something? Okay, simple, huh? Okay. So now, what is this? Now, if I look at that, you know, I mean, this resembles, so is a vector minus the model, okay, which is transpose, multiplied by the inverse of the covariance, and then it is x minus s theta. So it is the data minus the model, okay, then this is a vector, this vector is transpose, and then I have another vector of the error on the other side. And everything is balanced by the inverse of the covariance. So this one, you know, sometimes this is called the metric, okay, the quadratic metric, weighted by the inverse of the covariance. And this specifically, this there, you know, you can call it error depending on theta. So this is an error depending on theta, and that is an error transpose depending on theta. So overall, you know, what I can do is writing in a compact way. This is, this is a new writing in a compact way. Now, this, you know, this difference, so this or this one, this weighted difference, this weighted norm, okay, is not in general trivial to get. So my goal is to get if you like, I need to minimize, or for instance, to minimize, I need to calculate the gradient and set the gradient to 0. It's not easy unless I don't treat some very specific case. So, since it's not easy, I need to put into my numerical optimizer. So I need to design and to find an optimizer which is optimizing to find this minimum. Now, let's see a very special case for that. Now, let's see, for instance, the linear model. Let's assume that I have a linear model. So I take the general model and my dependency is h times theta. We have seen that this h times theta, so the linear model is, some cases, is representing a set of, a class of problems like the filtering that you have seen, last week, or we have seen together many times. So if we assume that, I have a linear model with the noise W, and the noise is Gaussian with a covariance that is known, then the maximum likelihood, can be written as the minimizer for x minus h times theta transpose CW and so on. Now, this one is good news, because this one, the kernel, is a quadratic form on theta. Okay? So that's a good news. So that means that if the model is linear, then the maximum likelihood is equivalent to minimize the quadratic form which is associated to the problem, where in my quadratic form the role of the matrix here in the center, which is, is weighting this difference, the role of this is taken by the inverse of the covariance of the noise. Now, let me explain a little bit what is the inverse of the covariance. To make it, before I make a new step, to make it, let me make a comment on that. So, what is the covariance? So the covariance CW, the covariance of the noise, which is this CW, is representing the variance of each noise sample and the correlation, the mutual correlation across the noise. So, we have seen during the exercises that we can, in general, we can take, for instance, a random process, and then, from the random process, we can calculate the autocorrelation. So, recall that, if let me write this, WK, WM is a random process, then we can write RWWK, which is the autocorrelation. Random process, which is 0 mean. We said that, random processes are 0 mean, except the exception is when I don't say 0 mean. So that is, we can calculate the autocorrelation. Autocorrelation, it can be autoregressive, it can be moving average, it can be Arnold, can be easy, can be complicated to be calculated, it doesn't matter. It doesn't matter. So that is, the autocorrelation. We can compute it. Now, so let's take the case now, let's go on the left and say, my vector W is, for instance, in a filtering problem, then my vector W is obtained by taking W1, W2, Wn. So this means that W stacks in the vector W, which is the vector noise, stacks n samples. Okay? So these are n samples of the noise. So this is sample 0, so sample 1, sample 2, blah blah blah, sample n. Okay? So these set of vectors is stacked, is plugged into a column. Now, if I want to get my covariance, well, how is the covariance in this case? Well, covariance, CW contains along the diagonal the variance of each term. So it is the variance of W1, variance of W2, variance of Wn. Okay? And here there is a covariance of W1, W2, and so on. And this one is the matrix is symmetric, so and blah 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 blah. All the terms, okay? Now, if the process is stationary, all these covariances, all these variances are the same. So, if stationary, what does it mean stationary? Stationary means that, the variance is the same in sample 1, sample 2, sample 3, sample 4, sample 5. And the covariance between two samples depends just on the mutual distance. So that means that if it is stationary, this is equal to, let me plug here. So if stationary, here I can find RWW0, and all along diagonal is RWW0. Okay, and the first entry here is RWW here in the first position. Now, in the first position, covariance of W1, W2, but this depends on just on the mutual distance, temporal distance between W1 and W2, which is one sample. So in position 1, this is equal to RWW1. And by the way, since all the samples along the diagonal, in the upper diagonal are the same, all the samples are RWW1. And because of the symmetry, the process is real. Okay, this is equal to RWW1, which is the same all along is lower diagonal. Okay. This is called upper diagonal, this is called lower diagonal. Okay? So, they're all the same. So, if I take the second sample, RWW2, and it's all the same here, RWW2, and so forth. So that means that my new matrix, which seems impossible to get, but this new matrix is just all the same along these diagonals. This one, this one, this one. Okay? So that means that cutting, if I cut on the other way here, if I cut here, I can see the distribution of the autocorrelation. Okay? But it's thriving in this way. Now, when the covariance matrix has this structure, we say that this structure that goes along the diagonal is characterized characteristic matrix, which is called Twelfth structure matrix. So what I'm saying is that when I talk about covariance, so when I talk up there, when I say covariance W is CW, it's a magic number. It's not a magic number, because if we are handling a stationary process, we can write it, provided that we know the correlation property, the autocorrelation of the noise samples. Okay? So if we know how the noise has been generated, and we know some correlation properties of the noise, we don't need to know specifically, it's simple. Then, at the end of the story, we can get the structure of the corresponding covariance matrix. So, it's not something that you cannot get. Now, this is the remark number 1. Let me make a second remark. Let's consider that our W is arbitrary, generic. It's not necessarily representing a stationary random process. W is general. Is not a set of samples coming from a stationary random process. So, and let's imagine that, these samples are characterized by CW. This is equal to just a diagonal matrix. Sigma 1, sigma 2, sigma squared n. Okay, so it's a diagonal. So it means, sigma 1 squared. Sigma 2 squared. This is the structure I'm talking about. So let's assume that, this is behavior. So what does it mean, the inverse? Well, the inverse of this one is, so CW to the minus 1. This is one of the cases where, the inverse is very trivial to get, because it's just the inverse of the entry of the diagonal matrix, which is equal to diagonal 1 over sigma 1 square, 1 over sigma 2 square, 1 over sigma n square. Okay. So now let's see what is the meaning for the inverse of the covariance put there in the middle. Now let me take this formula. Let me copy. So I'm copying this one because I want to understand what does it mean having the inverse here. And I do in this case because this is quite easy, but actually conceptually I can do there. Okay, so I don't know, I can do, let me do that, let me do it that way. I make it more general as possible. Let me do this, because this one is the most general. Yeah. Okay, so let's write this one in the extensive form. So this one means that, that is equal to the sum. Because if I write in extensive form, this is equal to the sum for k equal 1 to capital N of what? Of x k minus, I write as a subscript, which is more, sk minus sk depending on theta, square, multiplied by 1 over sigma square k. This is the writing in extensive form, exactly of that metric, which is the one that I'm minimizing. You remember, I need to minimize that one to get the maximum value. But what is the meaning for that? Well, this one is the variance K sample in xk. So this means that this is the variance of the noise of the k sample. Now, this means that this is the sum of the error. So it's the square of the error. So this is the error of the xk minus sk theta. So this one is the corresponding error. So it's the error on the kth sample that depends on theta. Okay. Now this error is weighted by the inverse. So this means that if one of the samples is very noisy, sigma is big. If sigma is big, I'm summing terms where if sigma is big, 1 over sigma is very small. So that means that if one of the sample of noise is very noisy, that sample counts less than the others. So I'm weighting by the corresponding confidence related to each of the xk, so each of the data that I'm measuring. So to summarize, if sigma square k is big, this means that k xk is very noisy. This means that, in the metric, epsilon k square theta is weighted by a small value, which is 1 over sigma square k. On the other hand, if sigma square k is a small, which means that xk is not noisy, not very noisy, then what I get is that the weighting factor which is 1 over sigma squared k. So if sigma is small, is big, is large. So the covariance placed in the middle is just weighting how reliable is each sample to be used for the estimation of the corresponding parameter. So covariance, is balancing. Now I can make this remark when the covariance is diagonal, because if I need to take into account also the correlation property, it's more complicated. So putting the inverse of the covariance there in the middle is balancing the degree of accuracy or the corresponding dispersion of each of the sample that I am considering for the estimation of parameter theta. Now, it's clear? So overall, what we have seen now before moving forward, we are seeing, first of all, that, what is the role, what is the meaning of the inverse of the covariance there, is take into account the different confidence level of different samples, data samples, in calculating the estimated theta by this metric. And the other is that if W is taken into account of a noise like in a random process, and my covariance is a tupled structure, if the process is stationary, is tupled structure, and has that specific shape. Okay? And by the way, once I know the autocorrelation of the specific random process, I can write the corresponding covariance matrix. So, after demystifying the role of the CW, So let's calculate the maximum likelihood estimate. So we were here, right? So we were at this point here. So we have a linear model now, and the linear model, okay, is this one, okay, so the maximum likelihood estimate is the minimum of this, but we know that this one is a quadratic form, and so we know everything about the quadratic form. So we know how to minimize this quadratic form. So we can write that this is a quadratic form, we can calculate the gradient with respect to theta, and set the gradient to 0. Now, let's see. So, I just copy, okay? So the quadratic form, now I minimize with respect to that, with respect to theta, and then this is the maximum likelihood estimate. So which is h transpose CW minus 1, h minus 1, h transpose CW minus 1, theta x. So my estimator, which is taking the data, is linear. Good news. Now, if I go back, I remember that I've seen this one before. It's blue estimator. So blue estimator is, is coincident with the maximum likelihood estimator, and since the maximum likelihood is the best, so why should I do something more? And that is the best. And in this way, I can also calculate the covariance, which is, we did it with the blue estimator, so I'm not repeating again. You have seen Friday. Basically Friday, you did the exercise by estimating the set of parameters in the filter, okay? And you calculate the covariance. And you just saw that the covariance is coinciding with this, and with this term, you don't know that this one is a Kramer-Rao, but we will see very soon that this one is nothing else than the Kramer-Rao one. So there is nothing, you cannot do more than that. That's the best. Now, life is not always that easy, okay? So of course, I started with a very easy one. Now, let's take another problem. The other problem is where the data x is obtained by this strange model. In this strange model, we have it's linear, but it's linear in a particular one. It's linear, but the regressor term, this h, okay, depends on another set of parameters. So we have our model that is, we have h that depends on a set of parameters that I indicate as omega, and then I have another multiplier factor that is alpha, plus w. Once again, to make the life easy, we assume that the noise is stochastic, is random, and Gaussian, and the covariance is known. Now, what kind of problem is this? Now, this model is very important in our, our semester, okay? Because this model is describing the sinusoid in noise. Now, let me recall you that. I want to be sure that it's clear. Where is the sinusoid? I don't remember which chapter. Fine. This one, okay? Just to recall you the model. In case I have a sinusoid with noise, okay, and these are the parameters: amplitude, the frequency, and phase of the sinusoid, and this is the amplitude noise. I can rewrite the model as if I have the data, and then I have the matrix H that depends on the frequency omega. And the matrix H contains all the cosine and all the sine in columns, so it contains two columns. And I have alpha 1, alpha 2, and you know, alpha 1, alpha 2 contains, you know, the amplitude and the cosine of the phase, and the amplitude and sine of the phase, just to recall you. So, and if I don't have a one sinusoid, but I have a multiple sinusoid, okay, that's it. So the model I'm describing is a model where I have my observation, and then I have a set of, you know, cosine and sine columns. So it's, you know, they go in pair. Okay, cosine and sine columns, and then here I have the amplitude. So amplitude 1, amplitude 1 cosine, amplitude 1 sine, amplitude 2 cosine, amplitude 2 sine, and so on. Okay. So that was the model. So this model, that is the one that I'm describing now, is the model that is used for a set of sinusoid in noise. So let me go back. That's how I described it. Okay. Now, but you know, this model is not only for a set of sinusoid in noise. This model is also used when I need to estimate parameters from a set of arrays, so a set of sensors, and my goal is to estimate the directional arrivals in a set of sensors. We will see that estimating the direction of arrivals, so it's like, what was that, the Wii was, you know, where you play tennis with a TV, right? Was that? You have an array of sensors at the bottom of the Wii game. Okay, so you hold the transmitter and you play with that, and the Wii is estimating your angle of arrival, so your position. And when you make a movement, you know, you estimate the dynamics of the movement of your transmitter, so that this is replicated in the game. Then it appears as if you are playing with in real, but it's all virtual. So anyway, so that is my model. So my model, you know, is depending on omega and alpha. Now, so this model, you know, omega and alpha are a set of parameters. So these are my parameter theta. Well, you know, my parameter theta they are different because omega frequency is hidden into the column of the matrix H, and alpha is linear. So if I need to look at the problem depending on alpha only, you know, that is quadratic. So if I freeze omega at a certain value, the problem is just a quadratic. So the way I'm solving is this one. So, you know, let me do it. So when I need to calculate the maximum reluctance, so according to the model, I just plug into here this one and this one, which is fully equivalent to that. So then, you know, looking in this way, the problem now is quadratic in alpha and is nonlinear in omega. No, so my goal is to minimize with respect to alpha and omega. Now, this means that optimizing with respect to alpha is a kind of easy. Optimizing with respect to omega, I need to see. Okay, so let's move forward. So, you know, this is a class of this depends. This kind of optimization problem is called separable because I can separate the optimization problem that is easy, quadratic, from the one that is not easy, omega. Okay, so you know, let's do the easy part first. So if I minimize with respect to omega, so what I can do, I can minimize first with respect to alpha, assuming that omega is fixed. So when I'm doing the yellow one, here omega is fixed. Since omega is fixed, means h omega is fixed. Okay? So I minimize that, and I mean, the minimization for that, so it's this one, but is a C previous problem. Okay? Because look at that. This problem with alpha, if you rather than alpha you have a theta, here it is. Okay? So that's the same. So now I can solve it because I know how to solve it. Okay? So, which is the same as the previous problem, which is here, except that there is a dependency on omega, which I don't know. Okay? I don't know, but I assume that I know when solving the inner part of the problem. Now what I do is I take this one and plug into there. Okay? Because now I know this one. So when I take this one and plug it there and there, okay, and I already solved it with respect to alpha, then I get the quadratic, so the quadratic. I get the norm, so I get the objective function, which is now depending on omega only. So when I put this into there, okay, which is a new alpha, then my output is this strange function. This p omega here is a projector. So that means that my optimization function is the data minus the projection of time x and blah 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 blah. Okay? I knew that it was not easy. So omega enters as a projector. No, but at least I remove my dependency on alpha. Now, what is the projector? The projector is this one, which is very complicated. And what it's telling is that, I need to minimize, so I collect X transpose system, so I need to minimize that. Now, if I'm in a very special case where the noise is white, it's similar. So the maximum likelihood frequency estimation is equal to X transpose projector on depending on omega X. What does it mean? Let's look at the meaning, the physical intuition about the interpretation of this optimization problem. Now, what is a projector? The projector is an operation which is taking the vector and projecting onto the span, onto the subspace of the column of what? Of H. Okay? So that means that this subspace depends on omega. Now, what is this subspace? This is the subspace. So let's represent in 2 dimensions. I have my vector of data. This is my data. This is X. Where is it? X. Let's look at this case. It's the same. Let's look at this case. So what I want to do, I want to take my X, project into X, project into the span of the column of H, and X transpose. Now, let me make one step more. This is equivalent to write in this way. This is X transpose P transpose omega P depending on omega X. This is equivalent to write that it is P omega X norm squared. Okay? Is the length. Now, what does it mean? Look to me. I have a vector. Okay, this is the data. So the data is x, is fixed. Now I have the subspace, which is the span, which is given by the column of the matrix H. To make it easy, our subspace only in 3 dimensions. Okay, so this is my measurement. So what's happened is the following: that I have this data, and my goal is to make the projection of data onto here as large as possible. Now, what is the projection? Now it's complicated. I have only 2 ends. Okay, what is the projection? The projection is, is taking the data, project, and is the length of this vector. Okay. Now I want to make this projection as large as possible. And what is varying is omega. And what does it mean varying omega? Varying omega means that when I vary omega, this subspace keeps moving. Remember, data is not moving. So data is here. Now, if, for instance, if the subspace is moving in this way, the projection is small, short. Okay? So this is going to keep rotating until, you see, the projection is maximized. So imagine that, I keep on moving omega. Okay? So I start moving omega, I make a projection. Then at a certain point, look, is getting almost coplanar on the same plane. Okay? That means that the length of the projection is maximum. I found omega. So the omega is the value that is maximizing the length of the projection. Length is square actually, but it doesn't matter. Okay? So it maximizes the length of the projection. The projection, and by keep moving omega. So when moving omega, this plane keeps moving until, I'm very close. That's omega. So, this is the meaning of that. So the meaning of that is that I want to maximize the projection of the data onto the span of the column of a matrix H, which is describing cosine and sine. Okay? And by the way, you need to look at the problem not just in 2 dimensions, but it's a multidimensional one. And so since it is multidimensional, it's not trivial to represent. Now, is it easy to get? Well, it's not that easy to get the frequency. Now, so since it's not easy, what do we do? Now, since the problem of estimating frequency in sinusoid is so important in statistical signal processing that we need to find a way to do it. Anyway, because it's important to estimate frequencies. And there are many problems where there are frequencies and we want to estimate frequencies with caps that are very one close to another. Frequencies in mechanics are representing the resonance of a structure, and frequencies in electronics represent oscillation, and frequency in space, for instance, represents the direction of arrivals in order to play with the wind. Okay, and the frequency in hydrophones represents, for instance, enemy that is approaching to us. If I have a set of hydrophones, and I can get the position where the submarine is coming, for instance. And directional arrivals, which is equivalent to frequency, is important for airplanes. Airplanes, we need to see where the airplanes are in the sky, and so on and so on and so on. So since the problem of estimating frequencies of the sinusoid is so important in statistical signal processing, that we need to find a way to get it. Now, we will see, so we go deeper later. Okay. In case I don't have one measurement, but I have a set of measurements, Now, the way to solve it is by simply, by collecting all the data. Now, let's write formally the problem. So assume that I have a set of multiple observations, and these are the multiple observations, and the model describing the noise, which is different from one set of data to another, okay? And the set of noise is described by the same statistical model with the same covariance, and the covariance is known. I'm underlining the story that the covariance is known because we can also estimate the covariance itself. And this means that the problem augments the covariance into the set of parameters to estimate, which means it's more complicated. Now let's see very elementary. So the PDF of all the observations, since they are independent, is the product of the PDF of each individual. So the distribution is the product of the distributions. And when I need to write a maximum likelihood, making all the simplification, I get that the maximum likelihood estimator is the minimizer of this function, which is where I sum all the errors, if you like, weighted by the inverse of the covariance. These are the errors. So it's the error of L equal 1, L equal 2, and so forth. So I'm making different experiments. In every experiment, for instance, is varying the model L, the model S, and the model is varying in a deterministic way. So we know how it's varying. But theta, the set of parameters, is the same. Now, let's see some simplification for that. Now, assume it's linear, and assume that the model is not varying. So, this means that every time I make a measurement, the only is varying is the noise. So, every experiment, noise is different, but the data is the same. Now, if this is the case, intuitively, what I can say is, in every experiment, I can estimate my parameters. Then I can average it. Assuming that I have a set of experiments. In every experiment, the model is the same, but the noise is different. So I can take one set of data, estimate the parameters, and then I can take these estimates and I can average the estimates. And this is exactly what is written here. So, this is my linear estimator, so I can make my theta at L, which is let me call this one as A, function A. So it is A multiplied by XL. Okay. So if I want to find the estimated value, what I do is the average for that. So I can take theta hat is equal to something L equal 1 capital L, and then it is theta hat L, and then I divide by L. This is the most intuitive one. So, every subset of data I can estimate the parameters, and then I do the average of the estimate. Now, is it optimum? Well, I can write the overall likelihood, I can write the maximum for that likelihood function, and then I can get the solution, which is exactly that. So, the intuitive solution, which is averaging the local solution, is coincident with the maximum likelihood. That's a good news. So, how is the covariance in this case? Now, I know that I know this is a common knowledge. I know, for instance, if I have a set of this is not in the specific problem. So, assume that I have AK, and AK is normal with the mean of A and the variance of sigma square A. Okay? And then what about if I consider that I have a set of AK, so a set of random variables that are statistically independent. And what about if I make sum of A, K divided by side of K over 1 plus. And I take the mean for that. So my goal is, what is the variance? Now, since they are statistically independent, the variance, this one, is the variance of each individual divided by L. So, let's prove it. So this one is, the variance of that head is simply, I need to calculate the variance of each individual. So, it is the variance of head is equal to the variance of the sum of K equal 1 to L of AK divided by L. But the variance is a quadratic, so it's it's involving a quadratic term. So this is equal to 1 over L squared, and I can calculate the variance of the sum again. But since they are all the same, the variance of the sum is equal to the sum of the variance. But they are all the same, so that is equal to sigma A. So that is L times sigma A squared divided by L squared, which makes it 1 over L. Okay? So when I'm averaging, and the result of averaging is that by averaging, like in this case, L terms, my variance is scaled by 1 over L, and my covariance is scaled by 1 over L. So everything else, as intuition is suggesting. Now these are taking. Now all the others here are quite technical, because these slides are taken from a part of that are taken from a course that the same course I gave abroad in another university, where they wanted to, or we made a complete discussion of a different setting. Okay, so my goal is to simplify a little bit here.
So, if I can ask a question, so Excel is every time a vector of L samples, right?
Yeah. Here, you mean? Yes.
We have every observation, so we have L data, a set of data, another set of data, and so on.
Yeah, you can imagine this way. You can imagine this way. That experiment is this. Let me make it practical. I have a signal, and in my signal, okay, there is, let's make the more general way, so it's not really. Yeah, it's this one, but I'm not going to discuss, but typical could be this one, okay? So you have a sinusoid, and you have a different piece of data. So what you have, we know that this one is a superposition of, 3 sinusoids. I don't know the frequency of this. So what I do is, I take this part, this segment, and this one is x1. Then after some time, I do another piece. This one is x2. And so forth. So I know that, the experiment has not changed. So I have the same sinusoids, but it's only that the noise is simply a different realization of the noise. So this is what I'm doing there. For instance, this is the nonlinear model. I don't want to discuss, but you are pulling me to discuss, but anyway. So the nonlinear model says, for instance, that I have a set of vectors, and each of them, this x1, is a set of sinusoid with the amplitude, and the amplitude is not changing. Okay, even easier. But you know, I have a noise W1, which is affecting this. And here I have a noise W2, and so forth. Okay. Now, in this case, you know, what I need to do is to, basically, I need to estimate one set of sinusoid with one set of amplitude.
In the Meccan average of all x, right? x1, x2, xn.
Yeah, I have many. X1, x2, xn.
xn.
Yeah, which is that one. Now, this case, you know, is resembling the other, but anyway, this is the kind. Or, for instance, as in the exercises that you did Friday, I have a system. And it was, what was estimating U or estimating G?
I think it was a channel estimation. So
G. Yeah. Yeah. So I have G and I have U. And I have, and there is some noise, W, and X. Okay. Now that was one experiment. Okay. And so in that experiment, you know, it was one. But what about if I get the input and I get the output? You know, this is the vector U1, and the output is X1. But you know, G is the same. So G remains the same. So in this case, I can rewrite, so, and then I have U2, and then I have X2 and so on. Okay. Now, for this specific setting, what I can do, I can write that X L, okay, is equal to, now in this case I want to estimate G, so I have a U L times G plus W L. So in this case, you know, G is static, it's the same. Okay? And so is my answer. So, I mean, we have a different setting, we have different experiment, different possibility to have some parameter fixed or some parameter variable. And by the way, this case doesn't fit in specifically in the first one. So it depends on case by case. Once you understood how to write a problem for one case, which is that one, you can extend the others.
And this kind of taking a lot of samples from time to time, we can do it in the case that the process is stationary, right? If our noise is stationary.
Yeah, yeah. The noise should be stationary.
Because otherwise we can't take a piece of data in.
Wait. If the noise is not, that's a very nice exercise. If the noise is not stationary, for instance, you know, I think it was in one of the old exams or homeworks. It was an homework, maybe it was some years ago. So the noise was not stationary; it was varying. The covariance was varying. So you have a set of data, like in this case, and the covariance was not fixed. In that case, you can also calculate the optimum G, because you need to put the corresponding covariance. And so, if you know the covariance, you can calculate the specific G depending on the covariance in every portion, in every cell. So this experiment, I don't know, might be this way. So we have a set of data, you know, but you know, at a certain point, the noise is growing. So this is the data. And then I have the, let me say, the variance of WK. And for instance, the variance of the noise is changing. Okay? And so if the variance of the noise is changing, if I take this interval, the variance is constant. If I take this interval, the variance is constant, but it's bigger. If I take this interval, the variance, you know, is that. So, in this case, I can describe in this way where I have, you know, my training in, and I also have the noise, which is varying, where the noise is varying the corresponding covariance, or, you know, if we are considering just the white noise, is only varying the variance of the noise. In this case, it's not stationary, the estimation. It's stationary within the interval of the capturing of the data. That's nice. So if I need to do that problem, I mean, if I need to estimate the parameter in this setting, so the variance of the noise is different interval by interval. If the variance is very high, then those data are not reliable. If the variance is very low, then the data are more reliable. And so it comes again, what I expect from this problem, if we write it in a stencil form, is that, you know, the sum of the estimate in each interval is weighted by the inverse of the covariance one with respect to another. This is what I expect. So going to the point, you know, what I'm saying is the following. We can consider different experiment where we put together different piece of observation in order to estimate a common parameter. It depends on case by case. So rather than doing all the casuistic, which is a taxonomic, you know, description where what apply in which case, you know, I prefer that depending on case by case, we try to reason on the problem and we try to solve it. That's my goal. So once I say that, you know, what I'm saying is, I'm not describing this part, even if it would be nice, but I'm not describing this part. You can read it, okay? You might be in a position where you need it, like in this case, you know, it's a sinusoid where, I mean, parameters are the same, but the noise is varying, but never mind. And another example is this one with I cut it. And the last example is this one that, you know, we will reconsider, you know. We will look at back this model later. Yes. This as well. Okay, let's have a break.